Evold, Daniel, how are you guys doing?
Oh, not much. I just actually had a meeting with Andrew Mobbs.
Cool. Which one was that? Was that the City of Medford one?
No, that is a guy who gonna help me with the resume and finding
Oh
them.
yeah, that guy. Yeah.
Yeah. Yep. So he said I should not concentrate only on that one because there's more than one actually. It's just the RCC has only pretty much this internship, but there's more than that one.
Oh, that's good to know.
Yeah.
That'd be so great. What an opportunity.
Mm-hmm.
Wish I'd have done stuff like that when I was that age. All right. Why is my iPad asleep here? Let's try that again. Share screen. iPad. Yeah, that was a good decision to try that again. All right, we are looking at impact today. This is cool. When stuff bangs off of other stuff. I got homework from you guys I saw in my email that I got to get in the grade book, and I'll get on that. Impact, how does that work? Let's have a look. So there's sort of two simple examples here. One of them is like a ball bouncing off a wall, that kind of a thing, like pool, the game of pool, bouncing off a rail, or a ball bouncing off a ball. I don't know if you played much pool when you were a kid, but man, we got addicted to that. We played all the time. Love that game. So we really want to look at both of those cases. And we actually kind of hinted at this a little bit the other day. And so now we're going to actually do it. And so here's what it kind of comes down to in its most interesting form. If I've got one ball over here, and we'll draw that a little on the small side. And then I've got, instead of a smaller one, let's make a bigger one. Just so that it looks more, it didn't work out too good, did it? Go away. So maybe you've played pool, and so if I hit the, well, let's hit the smaller one into the bigger one. Does it make sense you could kind of aim it anywhere you want to? And so what if I, let's see here, let's make a copy of this so it's perfect. So what if I sent this over here and it kind of hit right there? So I guess you could say then it was kind of following this path. Followed that path and it hit that other ball. The question is kind of what's going to happen as a result of that? Well, you certainly got our recent discussions of conservation of momentums, because the smaller ball, again, I drew it smaller so you can think of it as a smaller mass. It's not as well, it doesn't have as much momentum. Well, it depends on whether the other ball is moving. Like these could be banging into each other and both moving, as in the game of pool, if you just smack them. But to start with, and to keep it simple, if the second ball is not moving at all, so let's call this the kind of the A ball and the B ball. So the A ball is going to be the one that's actually in motion. The main question is, what's going to result from this? If they bang into each other, where's the A ball actually going to go? Where's the B ball actually going to go? And it turns out the most important part of this is kind of analyzing that point right there. And watch this really carefully. I'll try to draw this well. Right there. Yeah, I can live with that. Let me think. Can I live with that? Nope, I cannot. probably end up as the same exact line, but let's try it again. Maybe it'll just get better naturally. Yeah, it looks better. So it turns out the kind of the important part of this is not so much where the ball came from, although that matters. It's kind of how does it hit. So this point that I'll redraw as blue is kind of the point of impact. In a sense, if you think about it, does it make sense the B ball doesn't know anything except for it just got hit right there? It doesn't know where the other ball came from. Does it make sense if the other ball came from here or from here, any of those directions? The B ball doesn't know that. It got hit in the same spot in every case. It doesn't know that. So that's kind of interesting to think about. And that's what kind of makes this possible, I guess you could say, to make sense of. And so as it turns out, then that's the direction the B ball is going to go, no matter where the A ball hit it. Any of those cases, if that's where the point of impact is, then that's the direction the B ball is going to go. So it comes down to it. It doesn't matter where the A ball came from. You got to draw these two axes. That's what it comes down to. And so this one is often kind of in your questions in your assignment called the y-axis. And I'm going to, since I put y over there, I'm going to call that the positive y direction. And then this other axis, which is perpendicular to it, is the x-axis, and I'm going to call that the positive direction. Doesn't make any difference, but that's what you've got to establish. And in this case, these have names. And I'll draw this x-axis a little bit longer as well. But this axis right here is really important, and it is called the plane of impact, which I'm going to regularly be abbreviating plane of contact. The plane of contact. Plane of contact. So, and that's what I mean about the fact that the B ball does not know anything except for it was hit right there. And because that plane of contact is then established as the perpendicular line kind of between, if you look at these two midpoints right here, the two centers of these two balls, that's what establishes the blue line and the red line. And so the plane of contact is always going to be perpendicular to, well, this other line, which is called the line of impact, which I'm going to abbreviate LOI often. So you connect the centers of the two balls, no matter how the A ball got there, and that's going to create the line of impact, even if the ball A didn't come down the line of impact. You don't need to know this, but if the ball comes kind of straight at it and hits it, that's called central impact. In other words, it came right at it. A was following the line of impact, but this is coming off obliquely, and that's what's usually going to happen. That's the interesting case, is where A comes in at some angle, but it doesn't matter. The center line, the center points lined up creates the line of impact. Perpendicular to that through the point of contact is the plane of contact, and that's what you need to know to make sense of all of this in terms of where everything's going to go. And so B ball, however fast it goes that way, B ball is going along X. It's going to positive X in this case, no matter how ball A got there. The question, the more interesting question, is really what's going to happen to A? Is it going to ricochet back off of, and I want you to think about this, is it going to ricochet back off of B and kind of go over that way, do you think?
I mean, it should. Its y velocity shouldn't change if it's only experiencing a force in the x direction.
Yeah. And so that's what's kind of challenging about this. And so it looks like it might do that, but it actually depends on how big ball B is. It's actually not impossible that ball A would actually kind of go over this direction. In other words, it would hit it, but then keep on going. Like it would still have some forward momentum, and it might actually take off and continue following. Have you played pool? Sometimes that's the ball you hit, the cue ball will hit the other ball and it'll keep going forward instead of bouncing off and going backward. And so it's not real obvious is the point. It's not real obvious what's going to happen to ball A. It kind of depends on how fast it was going and how big ball B is. And some of those kinds of things. And so that's interesting. So let's draw a few more things in here. So we're saying this guy's coming in that direction. Okay, so cool. Now, Daniel just alluded to this. So let's just make a couple of points here that are not obvious. One, A's initial, that little O is initial, A's initial velocity in the Y direction. Notice that's so, man, what do we do with all those subscripts? It's like I have B and A, I've got two different balls, but then there's initial and final, like it has an initial speed and a final speed. And then we also got to look at, well, in which direction, in Y or in X. And so, there's more than one way I could write that. But I guess I'm going to write it that way. So the velocity of A in the Y direction, the initial velocity of A in the Y direction, and notice in this case it's negative. Is actually going to be equal to the velocity of A final in the Y direction. In other words, unchanged. However, the velocity of A initial in the X direction is going to be bigger than the velocity of A final in the X direction. It's going to change. Now, why is that? Well, that's because, and we talked about this a little bit last week, that's because some energy is lost here. Does that make sense? It's not going to bounce back as hard. And so, the conservation of, what is that called? The conservation of
Energy.
I'm going to say energy. But if I drop a
We're
ball,
assuming it's lost.
yeah, like you lose some of your energy in the impact. That's kind of what it comes down to. If I drop a ball on the ground and it bounces back up in the air, it is not going to get as high as it would before. And that's because some of the energy or some of the power, I mean, what word do we want to use, is lost in that collision, if you will. And there's always some lost. And so it's kind of a question of percentage. And that's kind of what that E number that we looked at just a little bit, we'll get into that in a little bit, but I don't want to confuse you with that right now. But what that E number is, it's like a percentage. In other words, you might get 90% of that back. And so some percent is lost, some percent is lost. And that's what that E value is. So let's just take a super quick look at those formulas again, because I showed it to you the other day, but that's this coefficient of restitution. And I kind of like that, as confusing as that statement is. Restitution, how much is restored to the ball that kind of bounces off. So the percent of energy remaining to rebound after a collision. And notice it says along the line of impact, which didn't make any sense before, but it's along the line of impact, this E value that's sitting right here. That's exactly what I just wrote in this note right here, which is in the, I said X direction. X is the line of impact. So you're not losing anything along the plane of contact. You're not losing anything, if you will, left to right here, if I'm calling Y left and right, but you are losing something when it bounces back. That's kind of the idea. So I remember hearing, at some point in my school, for instance, that the angle of incidence, in other words, let's say that hits at 40 degrees right there, when it bounces off, that will be 40 degrees. I remember hearing the angle of incidence equals the angle of reflection in a physics class, but that's not true. That's only true if Well, the collision is such that you don't lose anything. If you lose something, it's basically not going to bounce back as hard. And therefore, what's really going to happen in most cases, because it's hard to have a collision where you actually don't lose energy, this is going to bounce back at some smaller angle. Does that concept make sense? So effectively, the vertical version of my velocity. So if I call this velocity initial, and this bouncing back up is kind of my velocity final, that's kind of what I'm saying. The velocity initial is going to be bigger than velocity final. They're not going to bounce back at the same. However, that would be in the X direction. But if I said, well, what about the velocity initial in the Y direction? What is that doing relative to over here, the velocity in the Y direction? I guess I'll write it right there. Well, that's actually the same. Velocity initial Y is the same as velocity final. I put an O there, I should have put an F. The velocity final in Y. So nothing is lost kind of along the plane of contact. Nothing is lost in that direction. It's only lost in the bounce back, if you will. And that might feel good to you in the sense that, didn't we say before that, I drew this horizontally. We said that horizontal velocity is kind of unchanged, right? In other words, the velocity in the X direction, we said, oh, that always stays the same as if a ball is flying through the air, but the velocity in the Y direction changes due to gravity. Well, that's kind of true here, except for it's changing due to the loss of energy in that collision. And so I noted in those formulas kind of at the bottom of that E equals 1, in other words, 100%. E is a percentage. So if it's 100%, you get all your energy back. That's called an elastic impact. You don't necessarily have to know those terms for our problems, but energy is actually conserved, and that really doesn't happen. That would solve the energy crisis if we could bounce a ball and it would just keep bouncing forever and never stop. So realistically, though, you get some percentage, maybe 90%. We're going to do a project on this and kind of play around with it together and before the next test, probably a week from today. You could lose all of the energy. Does it make sense if you took a hacky sack and dropped it on the ground? It just gets absorbed and lands on the ground. It doesn't even bounce back up in the air at all. Or a lump of clay, I could drop that. It just sticks on the ground, doesn't bounce up at all. And so you're going to realistically lose something. You might lose everything. If it's a super ball, you're going to get a lot of it back because it's more elastic, but it won't bounce as high as it was. And so the best you can do is whatever, 98% or something like that. Maybe that'd be the best if you had a nice hard floor and a really good, well, elastic sort of a ball. So, okay, that's a fine introduction, but we need now to go do a problem. Try to make some sense of all of this. See if there's anything else I wanted to say. So the only thing I will say is what we learn from this, besides just kind of how to set all of this up, is we need to separate out what's happening in the X direction and in the Y direction, or I guess I could say the velocity of X and the velocity of Y. I've got to pay attention to that differently. And again, what makes X and Y is not horizontal and vertical. We're not talking about horizontal and vertical here. We're talking about X and Y, where the X is intersecting of the two circles. And so anyway, let's take a look. Let's do one that's got a ball in it. Let's see. Let's do that one first. So this is kind of cool because this is a somewhat realistic example in the sense that this is the game of curling. So pool ball is a kind of good example too. But notice they've drawn in here for us. They've already drawn in the line of impact and the plane of impact. They already showed them running into each other. And so it's good that we're seeing this arrow right here, because I just want to give you time to soak the problem in. So here, there's B sitting there, not moving. B is just sitting there. And then here comes A along the green arrow, smack. As soon as it hits it, bam, there's the point of impact. That's always going to line up through the center of the two circles. And you just established your x-axis. Now, because they put X, because they labeled X down here, I'm going to call that positive X. Doesn't matter which way you call it, but I'm going to call that positive X. And then perpendicular to that, if I draw another line through that perpendicular, then that's Y. And again, they put Y over here, so I'm going to call that positive Y. It doesn't make any difference. It will save you confusion if you always call the X the line of impact. And you always call Y the plane of contact. But it doesn't really matter. And the only reason I say that is because, you know, we've got little formulas about how V of X, V of A, the velocity of A in the X direction will change, but the velocity of A in the Y direction won't change. And so if we mix up X and Y, then we're going to kind of get confused by doing that. So anyway, this thing comes in. Notice they say velocity of A1. So that's another way to do this instead of saying initial and final. I'm going to switch that to initial. Velocity of A initial is coming in at 8 feet per second, and everything is wonderful. And I'm sure they'll tell us in this problem that those are smooth, meaning they're not slowing down. They're sliding on the ice, which is, you know, pretty frictionless, but they're probably going to tell us it's, you know, smooth and we're not losing any velocity. So here it comes in at 8 feet per second. So it's got momentum because it's got a speed, a velocity, and it's got a mass, and then smack, bangs into B. And so what we said a second ago is that B is definitely going to go that direction. Does that make sense? Doesn't matter what angle A came in at, it's going to take off perpendicular to the plane of contact, perpendicular to that. It's going that direction. But of course, the question is, how fast is it going? And then of course, where is A going to go? Is A going to bounce back and kind of, you know, head over this way, or is A going to kind of continue on because it has a lot of momentum and kind of push on through and keep going? And that's really what we're after. And you can appreciate that's complicated. I mean, isn't it amazing that people found a way to kind of make sense of all of this and actually figure it out? And of course, I find myself wanting to try this, don't you? Like, I want to hit a pool ball, like make all the predictions and kind of see if it'll do what we say it's going to do. So let's see, what are we told? I tried to introduce it a little slower. Slides over the ice. So A is the moving one, B is the not moving one. So they both have the same exact weight, 47 pounds. Notice they threw the word smooth in there, meaning it's frictionless. And the coefficient of restitution is 0.8. So we're only retaining 80% of our velocity. That's all that means. If it comes in at 100 feet per second, then it's going to come back out at 80. So that's kind of cool. And so they say determine their speeds just after collision. And we're told, as I said a minute ago, that A is moving at 8 feet per second, B is at rest. And so, okay, cool. So from this picture and the fact that that's a 30-degree angle, again, what we've got to come up with here then is to kind of figure out what's going on. We got to break things. We got to separate things into X's and Y's. And so the first thing I've got to learn here is what is the initial velocity of A in the X direction, and what is the initial velocity of A in the Y direction. Again, I don't really know how to write that. It seems weird to have 3 subscripts. So X direction. So maybe you need to draw yourself a little right triangle, and it would be easy to draw this incorrectly, but if 8 is your speed, then the 8 is going to be the hypotenuse. And so this down here is going to be my velocity in the Y direction because it's pointing parallel to Y, and this is going to be my velocity in the X direction. And then I was told this angle here is the 30-degree angle. So now I can see what to do. I can say 8 times the sine of 30 as we've done many times in this class, is going to give me my velocity of y. So I pound that in there and I get 4 feet per second. So that's my initial velocity in the y direction. Half of it, if you will, is going in the y direction. Is that positive or negative based on the sign choices that I made here? Because you can't get this wrong and it is important. So in order to create the vectors, I had to go head to tail with these 2 red vectors. And so it's pointing in the positive y direction thanks to my picture. So it is 4. And then my velocity of x would be the same, except for it would be 8 times the cosine of 30, which is I'll call it 6.93. Is that sign correct?
No, should be
No.
negative.
That's right, because I called this direction positive x and it's going the other way. So that's actually negative. Again, if that bugs you, then go change positive x to the other side. Maybe there's an argument for that because it's, you know, in the direction of travel. So, but it doesn't make any difference as long as you just pick something and make sure you note it and then you're careful. And of course, you can't get this wrong because a negative velocity versus a positive velocity is going to tell you which direction it's going. And so you got to establish that. So that's really important not to screw up. So, okay, I understand what's happening. And so from what we just looked at a second ago, then the interesting one is not the velocity in the y direction because it's going to stay. In other words, this, we just said a second ago that if the velocity in a in the y direction is 4, then it's going to stay 4 even after it smacks into it. So if I say velocity final of a in the y direction, they're the same. It hasn't changed. A is going to keep moving to the right just because it pounded into it. And again, the way you want to look at this is a doesn't know that it just hit a ball. A thinks it hit a wall. And so if a is coming in here like this and it goes bang, then it's going to bounce off and just kind of keep going to the right. It was going to the right from the start. It's going to keep going to the right. No change. But a of x, much more complicated. And so here's where we've got to get kind of creative and get our conservation of momentum. And all I really care about here, since we said these are equal, is our conservation of momentum in x. I only really care about what's happening in x because in y, I already know what's happening. It stays 4. And remember, that just meant the sum of the initial mass times velocities is going to equal the final sum of mass times velocities. So the masses don't change. But again, we got 2 balls here. The 2 balls or stones have an initial momentums and then they have final momentums, and that's not going to change. Again, that's because they're smooth, because we didn't lose anything in terms of gravity. Now we lost things in terms of impact, but we didn't, or sorry, friction. We didn't lose anything in terms of friction. So the only thing that's kind of, I don't know if boring is the right word, but simple about this is B didn't have any initial momentum because it isn't moving at all. So, but they could be both moving toward each other and then bang and then bounce off in totally different directions, which is really kind of cool to consider. So let's consider all of that. Then what would that equation look like if I kind of wrote that out? So this is my first equation. So let's see, I got A, so I've got its velocity, its initial velocity of A in the x direction, which we already know is 6.93 times its mass. I should probably put mass first, I suppose, since we usually do, but it doesn't really matter. And its mass, notice it says 47 pounds, which remember is not a mass, that's a force. So I actually have to divide that by 32.2. And it may go away. Remember, we talked about that, a lot of these problems that kind of goes away. So there's the initial momentum of A, and I'm going to go ahead and write this down, but the initial momentum of B, 32.2, initial velocity of B in the x direction, that isn't moving because it was at rest. And so I could have just left that off. And so all of the initial momentum, if you will, is because A was moving. It should make sense to you. But then they bounce off, and this is where things get interesting. Well, nothing changes size. And so I have all the same masses, but now I have velocity final of A in the x direction and velocity final of B in the x direction, because now they are both going to be moving. So if you will, some of the power or energy that A had is now imparted to B, but collectively they're the same as they were from the start. But we don't like this equation. We don't like this equation at all. Well, we don't mind it here because we know this was negative 6.93, but we don't like this at all because this is one equation, but with two unknowns, and that's not good. Two unknowns. Bad news. So how am I supposed to figure this out? And this is exactly where we got kind of stuck in the introductory problem that I mentioned the other day, where two balls kind of banged into each other. Like, what do we do? And this is where that coefficient of restitution equation comes in. And so let's stare at that in a little bit more detail. I'll rewrite it in a little bit, but notice I use the language on your book uses ones and twos for this, and that's okay. In case you happen to look there, they call, initial one, that's like time one, and this is time two. There's nothing wrong with that. That works fine as long as you recognize. But I kind of like initial and final because you see that in physics a lot more. And it actually doesn't matter. Notice this is like ball B and ball A or something like that. It actually doesn't make any difference which one is which, but it helps to keep consistent and think of A as the one that's kind of coming up and hitting the other one. But remember, they both might be moving. And so that's kind of my equation I've got to work with. And so that's really kind of complicated. But let me just say one thing that's kind of interesting about this. What if B was a wall, meaning it was not moving, and after you bounce into it, it's still not going to be moving? Does that make sense? If that's the case, this equation would be, well, 0 minus the velocity of A final, and then velocity of A initial on the bottom minus 0 again, because the velocity of the wall initial isn't moving. And so you really just have negative velocity final over velocity initial. Why does that actually make sense? What makes sense about that? I just want to make sure you kind of understand how simple this really is.
Well, if the wall isn't moving in the end or in the beginning, then the value we're really getting here is just how much of the kinetic energy is maintained from bouncing off the wall.
Yeah, that's exactly right. In other words, if it came in at say 11 and then it bounced back at 9, of course it's going to be less, right? So the final is always going to be less because you're always going to lose energy. So it came in at 11, bounced out at 9. So that's where that percentage comes from. In other words, it really is just a simple percentage. That particular number right there is like 81%. And so you lost 19% of your momentum thanks to the wall. The wall absorbed it because of how plastic or how elastic the impact was. Again, based on the material that the wall's made out of. In the case of pool, the bumpers are kind of made out of rubber, so they're a little more springy. And of course, what the ball's made out of. And so this is just a percentage. If it comes in at 9 and bounces out at 11, that's it, simple. Coefficient of restitution is 81%. What's with the negative sign though? Why isn't it just 9 over 11? Why is there a negative sign there? Well, if it came in at 11, doesn't it actually bounce off at -9? In other words, it got rejected, right? It got sent back where it came from. So if it came in at +11, it's actually going to bounce off at -9, which would be a negative number. So by switching these around up here and putting B in front of A and then A in front of B, they're making a negative sign appear here. And if a negative sign appears, it'll just take the negative sign away that naturally comes, and then you'll just get a positive percentage. So it'd be weird to say, you know, the coefficient of restitution is -80%. So anyway, it's just a little intuition about kind of why this formula works the way it does. But let's bring that equation in and put it to use. Of course, as always, you are going to have the access to this for your test. That's not the right world. So we need a second equation. Unfortunately, it's the coefficient of restitution equation that is going to give that to us. So let's bring it in. So I'm going to put that thing down just so all I get is what I want. So there's my second equation. So I need 2 equations and 2 unknowns that I can handle. And so, okay, great. We were told in this problem that the coefficient of restitution was 80%. So that's known. Our velocity of B final, and remember, this is, again, only true in the X direction. So this NX business here is extremely important. This whole formula for coefficient of restitution is only in the X direction. So I've got the velocity of B in the X direction, which is the same one that I wrote up on top, minus the velocity of FAX. So those are the 2 that I don't know. But down below, I do know those. The velocity of A initial in the X direction, I'm going to go ahead and write that out. Velocity of initial of A in the X direction, we knew that. That number was the -6.93 number. And minus the initial velocity of B in the X direction, that ball wasn't moving. And so there's my second equation. So now I've got 2 equations and 2 unknowns. So I'm now happy. So that's kind of key that comes out of this mess. And so, okay, great. Let's solve those 2 equations, 2 unknowns. Again, we've done that a lot. You may have your different methods for doing so, but if you solve that system, I think I'll just move down here and switch colors. You end up with the velocity final of B in the X direction as being -6.24 meters per second. Since this problem is, no, this is feet per second, isn't it? Yeah, feet per second. And again, notice that tells the whole story. In other words, we already know what direction B is going. It's going that direction. It's going along the line of impact. And so we know where B is going. Notice it's interesting, but it's got most of the force. Like how much was brought in? 6.93. Whoops. 6.93 came in from the initial ball, and most of that, 6.24, was transferred to B. So it's like B got it all. That's kind of interesting. So I'll just make the note here along the line of impact. So I'm done. I know that one. And notice again, the negative is really important for that. And that's why the sign of all of that is important, because it tells us that it's going the direction it would have to be going. We called positive X this direction up here. So of course it's going to go away from that. It's going to go away from the impact. So darn well better come out negative. But of course, where it gets interesting is the other calculation. What happens to the velocity final of A in the X direction? Well, that comes out negative 0.69 feet per second. What does that mean? What does that mean happen to it then? As far as its X direction, it's like negative 0.7. Did it bounce off kind of like over here somewhere? Kind of looks like it would do that, doesn't it? The answer is no, based on the calculation we just made. Do you see why? If it went in that direction, isn't that in the positive X direction? We didn't get a positive X, we got a negative X. So it's not doing that. It's actually kind of going over here somewhere. Does that make sense? It's following it. It actually kept going. It hit the other one and then kept going. It didn't bounce back. So it makes a difference if it's hitting a wall where it is, of course, going to bounce back, or if it's hitting something else. In this case, they're the same exact weight. So notice how unclear it is as to what's going to happen here. So the math here is essential to kind of figure this out. So that's kind of surprising, I think. So let's kind of draw a picture of what that means. So if this is ball, so if this is A, and we said this was in the positive Y direction, I think, is that what we said? Then we said the X in the Y direction, this velocity was conserved. In other words, the velocity final of A in the Y direction, we said it didn't change. It was that 4. It's going to stay 4. So it keeps going 4 that direction. But we found out that its velocity final of A in the X direction was actually negative 0.69. So collectively, what is this thing really doing then? It's going 4 in that direction. And if I connect the arrows head to tail, it's going negative 0.69 in that direction, so that it's the actual velocity itself, kind of the velocity final of A, not in the X or Y direction, but just its actual velocity. It's actually going in that direction. So that's interesting. So it's bouncing over here somewhere. It's actually following it. And from these vectors, I can see that I'm going to use the Pythagorean theorem on 4 and 0.69 to come up with that answer. So velocity final in the A direction would be negative 0.69 squared plus 4 squared, all square rooted, which works out to be about 4.06 feet per second. So that's actually its velocity. Not in X, not in Y, it's in velocity. And of course, it might be interesting to know, what angle that is too, because I mean, that's, if you report the velocity is 4.06, you can understand somebody wanting to know the actual velocity, but that by itself doesn't do any good unless you can kind of say what direction it goes. That's the advantage of leaving it as 0.69 and 4, because that actually tells you how hard it's working that way. But of course, we could just come back in here, and since we got a picture for this, I could throw theta in there. So it's kind of like, how many degrees is it measured off of the y-axis? And I can see that tangent would take care of that. So I could say the tangent of theta equals, notice I'm getting rid of the negative sign. And I'm doing that because I have a picture that shows theta is, positive or negative. And if you do that, you get theta is approximately, you get 9.8, but approximately 10 degrees. So now I kind of know everything about it. I know exactly where it's going to go. That's kind of cool. So to kind of throw it back in the picture up here, if I don't completely ruin this, then I know B is going to kind of head over here. And we said that was going to travel at 6.24. So let's put that in this picture. So that's where B is going to go. And then we just saw that this is the velocity of B final. And then we said, hey, it's actually going to go over there, roughly 10 degrees, and be going at 4.06 feet per second. That's what's going to happen after these two bang into each other. And it's kind of cool that you can figure that out. So again, I find myself thinking, okay, great, let's go roll some stones and see if that's actually the case. That's pretty powerful. How's your brain? So I hope you can see how essential it is to kind of separate as we did for conservation of momentum. We got to separate X and Y. This is essential. Take a few laps around it. If we don't do that, we're definitely not going to make any progress with this stuff. And it produced two equations, two unknowns, which we don't mind. Armed with that, why don't you guys try this one? This looks a little easier. Only in the sense that they rotated the figure so that the X is horizontal and the Y is vertical. So you don't have the axis isn't all twisted. So that kind of feels like it might be a little bit easier. So notice they kept the convention we talked about. In other words, if you line up the two balls right here, the x-axis is the line of impact. So we know B is going in that direction for sure. This is going to be the velocity final for B. It's going to be going in that direction. And again, because they labeled it this way and because it's nice anyway, like right is usually positive and up is usually positive. And so that kind of makes sense maybe to call those the positive directions. And so let me give you a second. Notice this is really the same question. The only difference is it's metric, which means I don't have to convert the mass. It just is what it is. However, notice it's 200 grams. That's important. Although again, it might cancel out. To make sure you got off in the right direction, did you say that 1.5 times the cosine of 40, cosine's adjacent, that would be the velocity of A initial in the y direction? And since it's going the opposite, it's actually we're gonna call this a negative number. So 1.5 times the cosine of 40, see if I already did this. Yeah, 1.1, I'm gonna call it 1.15. But it would be negative, and so that's my initial speed in the y direction. And my initial speed in the x direction being sine would be 0.964. Let's call it 0.96. And it's also going negative relative to what I call positive. And so part of me thinks, "Oh, I don't like negative numbers. I think I'll switch those positives and negatives." I'm not going to, but just because you like to call right positive and up positive, that kind of screwed us up in this case. So you're free to pick those to be anything you want. You just have to inform me if it's a test, which one is which.
I think I maybe messed it up, but final velocity of B in X, I got 0.94 meters per second.
Let's look at it. We're gonna run out of time if I don't.
I got negative 1.063, so a bit higher.
Mhm.
That's good. We got different answers. This is weird how this is kind of not hard and hard all rolled into one.
I think I didn't. Did you put original velocity of AX negative 1.15? Is that what you did?
Yeah, well, technically I actually used negative 1.149 because that was just in Desmos, so it's easier
Yeah,
to
I
be
think
more precise.
I just forgot the negative out there.
Yeah.
I don't think it should affect the magnitude though.
Mm,
It just means that in later equations, which variable you solve for shouldn't make a big difference.
Let me show you something interesting here, just as a kind of a side note to kind of, I don't know, prove something to you, but you don't need to do this, the conservation of momentum in Y. Let me show you, well, why. Because you have the mass times velocity. So our mass is 0.2 kilograms times the velocity of A initial in Y. So mass times velocity plus 0.2 times velocity of B initial in Y. So they both have a speed and a weight initially, and then that'll be the same as when they pop out the other side. So velocity of A final in Y plus 0.2 times velocity of B final in Y. But look at the picture. This is just interesting. You don't need to do this. Let me show you why. The way B moves, the velocity of B final in Y is actually going to be 0. Do you see that? Because it's not going to move in Y. That's why you arrange these axes this way. It would be very hard to solve this problem if you had the axes not be lined up like this. So it's going to cruise right along X, therefore it isn't going to have any velocity in Y. And because it was at rest, it was also just sitting there. And so this is what I told you at the start. I just asked you to believe me, but notice if you line the axis up this way, that means the initial velocity of A and Y is going to equal the initial velocity, the final velocity in Y for A as well. They don't change. It doesn't change in Y. I just kind of told you that that was true, but this is kind of Y. So that's why you don't usually need to write that. What we do need to write, however, is conservation of momentum in the X direction. We definitely need that because they're not going to stay the same. And so I can go through the same gyrations. And I've showed you this before, but I think this is a really good way to do this. I think it's awesome to write the whole thing out with kind of all the formula in it. Velocity of A final in X plus 0.2 times the velocity of B final in X. Like write that whole thing out and then come back and lightly go over it and say, oh, I know what my initial velocity in X was. It was negative 0.96. So that's known. I know my initial velocity of B in the X direction because it was a rest. And so that's it. And again, you're more than welcome to divide. If you were going to solve this by hand, you're more than welcome to divide 0.2 out of this because the mass didn't make any difference since they were equal. So there's my one equation, one unknown. My second equation, though, is going to be that E value, that coefficient of restitution. And we said that was equal to, I got to look that up because I find myself not remembering it. Let me see, can I still just paste that in there? I'll just paste it in again, why not? So far, is this what you did? So I'm going to say our sort of our third equation involving E looks like this. And I'm even going to crop that top part of it out this time and maybe make it a hair bigger. And so then I start plugging in for my second. Well, I'm going to write out, and it would maybe not even be a bad idea if I had X's in all of these, like every one of these is in X, because that's the only direction in which they're not the same. So those really kind of should be all X's. So the top two, I don't know, but the bottom two, I do know. What was my initial velocity in A in the X direction? That was negative 0.96. So I'm replacing this with negative 0.96, and my initial velocity in B, because it was at rest, is also just sitting there at 0. And E, we were told in this case, was 0.85. We got a little bit more back on this problem than last time. It was only 80%, but this time it was 85%. And so now I got these two equations, two unknowns. I'm gonna go a little slower this time and kind of just do them myself. So if I did divide both sides by 0.2, my first equation up there is negative 0.96 is going to equal velocity of A final in X plus the velocity of B final in X. And this second equation that I just got, if I multiply 0.96 times both sides, 0.96 times 0.85, I get negative 0.816 equals velocity of BF in the X direction minus velocity of AF in the X direction. So there's my two equations, two unknowns. And I see that in this case, because I took the time to do this, I can actually just add these together. Because if I do that, then here's a positive one, there's a negative one, this will just cancel out. So on this side, I get 2 of those velocity B finals of X. And if I add negative 0.96 and 0.816, I get 1.776. And so all I gotta do is divide that by 2. And so I don't need to cheat to do this. So my velocity of B final in the X direction is 0.888 or 0.89. Was this metric? I forgot. Yeah, meters per second. And I'll add the note this time. This is along the, and it'd be negative. I forgot the negative. Along the line of impact. I don't remember what the question was, but I know what it's going to do now. Notice that's not very fast. But remember, the initial ball wasn't coming in very fast either. It was only coming in at 1.5. So anyway, I don't think I screwed that up. Okay, cool. Well, now that I know that, then can't I plug that back in, if you will, say back into that top one up there, and then I'd be adding it to the other side. So I'd have negative 0.96, but then I'd be adding 0.89. So then that leaves my velocity of A final in the X direction being negative 0.07, which feels wrong. Is that wrong? Feels very wrong. Did I do something wrong? I didn't get the same answer I got before. I think I did something wrong. I'll stare at this for just a minute. Yeah, I did something wrong clear back at the top. I got to go fix a couple things. I mixed up sine and cosine. Cosine of 40 is adjacent, so my cosine answer was my x answer. I'll leave these as a different color since I screwed them up. This was my x answer and this was my y answer. So I grabbed the wrong two, and so this is really equal to velocity of a force.
I did that too.
Good, good. I don't want to be alone. It's an easy mistake to make. And as I've often told you, I kind of like to make mistakes like that in front of students just because, in my case, the only reason I thought I did something wrong is I get such small answers. So that means if I go down here that I should not be plugging in negative 0.96 right there. I should be plugging in negative 1.15. And that's all fine, except for this answer here is negative 1.15. And I would have needed to have fixed it down here, negative 1.15. So this So that means when I multiply 1.15 up here times 0.85, I don't get the answer I got. I get 0.9775. I'll call it 0.978. So that when I add these, negative 1.15, I get negative 0.172, much smaller number. Actually feels wrong too, for some reason. Maybe I'm going too fast.
I'm getting negative 0.94. I don't know if someone else got the answer like that.
For which one did you get? Velocity of A final?
For the B final.
B final. So, let's see, I made yet another mistake. So if I add those negative 1.15 minus 0.978, I get negative 2.128. When I divide that by 2, I get 1.064. So this is now finally correct. For B, negative 1.064 feet meters per second. So that's actually correct. I didn't make another dumb sign mistake. So then if I put that back in above as a negative number, and then I add it to the other side, since it's negative 1.15 plus 1.064. Does that not look right? So I got velocity, I think I'm doing okay. 0.086. But that's the force of A in the X direction. In other words, it's barely moving in the X direction. And from above, the velocity of A final in the Y direction has not changed. It's what it always was, which was negative 0.96. So if I do the Pythagorean theorem on those, since 0.086 is so small, I'm not really going to get that much of an answer. So if I use the Pythagorean theorem on those two, then I'll get velocity of A final in no direction whatsoever is 0.97. So yeah, I agree with you, Evan. And since that's the case, if you wanted to know kind of which, again, what direction that thing is going, I'll draw this a little not to scale, but if this is A right here and it's moving left 0.086 and it's moving down a lot more, negative 0.96, then that being its velocity of A final, that's why Pythagorean theorem was involved. But if I wanted to figure out what angle that was at, what angle it was traveling at as a consequence of that, I could pick whatever angle I want. I guess I'll pick this one up here. So then I could say the tangent of theta would be equal to the opposite 0.96 over the adjacent 0.086. Notice again, because of the picture, I'm just cleansing it as its negatives. Second tangent of 0.96 divided by 0.086 is, need to be in degree mode. I got a radian-like answer. 84.9 degrees. So that's its direction. So roughly 85 degrees. So if I go back up at this picture, then that's kind of cool to sort of note. Now that I draw it up in this direction, I find myself wanting to use the other angle. So it's actually going to take off in that direction according to my picture. Oh, that's right, 80. Yeah, that's right. So not much of an angle. So my theta is really up here. So this angle here is like 85 degrees. That's the direction it's going. And 0.97 meters per second. In a sense of the picture, that's what's happening. So again, just like last time, it's actually following it. It's not bouncing off kind of back in the direction from which it came. It continues to keep going forward or along the line of impact, kind of like you might not expect. Because this is so cool and it's not hard, but you obviously, I mean, I just demonstrated it's really easy to kind of mix up something and kind of screw it up on a test to make sure your work is clear in case you do something dumb and you don't catch it, because I'd like to be able to help you, give you as much points as I can. But what I'd like to look at tomorrow is what if the ball bounces into a wall? That's actually easier. What if it bounces into a wall so that the second ball isn't a ball, it's a wall? And the other thing I'd kind of like to play with is what if two balls were not traveling directly toward each other? Because if they do that, they're just going to bounce back in the same directions. But what if they were slightly off, like this? And does it make sense if I moved them too much, they would just pass each other and never hit at all? Or, maybe it's even more interesting, like if I put this ball up here and kind of send it down that direction, and this ball over here, but I send it in that direction, it'd be a timing thing. But where these actually hit, could I figure out what was going to happen, especially if they had different velocities, different weights, the key is just getting them drawn like this so that I can establish, hey, there's the plane of contact and there's the line of impact. And so now I know how they're going to behave. That's my new XY axis. I just have to get them to run into each other, and then I can kind of go from there. So I want to play around with that just to see if we can still survive that. The cool thing is with both of them having initial velocities this time, then they're both going to have momentum. So there's going to be a definite initial momentum and a definite final momentum. That just seems kind of fun to play around with. And of course, we're talking about here is more like a car accident or something of that nature where, one is not just sitting still. I think your sitting still questions in your assignment are fine. Like you're okay. This thing sit still. But it'd be kind of fun to get them both moving, I think. The interesting thing about the last drawing that I made, though, is where they actually bonk into each other would totally depend on time. Because if this ball on the left moved a little bit further to the right, in other words, I waited to release the second ball, then when it hits, it's actually going to hit kind of in a completely different location and make a completely different XY axis, like where they're actually going to hit. So it's kind of interesting if they're kind of heading in different directions, kind of like a car crash. And so that might be fun to play around with. I don't know. We'll see what I come up with before then, but all I really want to do is just help grow your intuition on this. So we'll worry about that on Thursday. So my intention is, I don't know if you looked at the syllabus, but to kind of play with this idea some more and just kind of go beyond what's in the book and deepen your understanding of it a little bit. And then we're going to do a project on Tuesday, and then you're taking a test over everything we've studied since then on Wednesday, kind of on your own time, and then we'll go somewhere else. So that's the plan. All right, go out in the sunshine.
All right, bye, y'all.
All right, see ya.
See you later.
Yeah.